Okay, so optimization is pretty rarely tested in actual exams, so I was only able to find this one. So we'll just attempt this. It's a two-part question, so let's look at part one. So the diagram shows a badge made of thin sheet metal consisting of two semicircular pieces, centers B and C, each of radius x cm. They are attached to each other by a rectangular piece of thin sheet metal ABCD, such that AB and CD are the radii of the semicircular pieces and AD equals BC equals YCM. Given that the area of the badge is 20 cm squared, show that the perimeter, PCM, of the badge is given by P equals 2x plus 40 over x. So usually optimization takes two equations and you have to get the other one based on what you know with the first one. So the first one, we're given the area. So this whole thing over here is 20 cm squared in area. That means to calculate the area, we should actually break this into separate parts because as a whole, we can't actually find the area. We have to break it up into part A, part B, and part C and find those areas individually and add them together. So let's look at part A. It's x cm, it has a radius of x cm, which means that its area is equal to pi x squared. But it's a semicircle, so it's half of that. But there are two semicircles, as we see over here. So the half and the multiplying by 2 cancel out to give a C and A combined is pi x squared. That just makes it faster for us. Now, if we're looking at B is obviously just xy cm squared. Well, we know now that pi x squared plus xy is equal to 20, based on the fact that they told us that the area is 20 cm squared. But we have to find the perimeter. So now let's look, based on x and y, what the perimeter is. So this length over here, A to, I don't know, let's just call this E. This point's E. We have to find that first. So the circumference of a circle is 2 pi r. So we've got two different halves of a semicircle, and together the circumference is 2 pi r. So it's 2 pi x actually, because the radius is x in this case. So P is equal to 2 pi x, and then we add it to this length and this length, which is just 2y, and then we add it to this length and this length, which is plus 2x. But we need it in only one variable. In this case, we need it in terms of x. So let's isolate y. So y, in this case, we can see is 20 minus pi x squared, which is equal to xy. So y is equal to 20 over x minus pi x. And we can substitute that back in here. Let me go down so we have more space. So our perimeter is 2 pi x plus 2, and then we insert 20 over x minus pi x plus 2x, which gives us 2 pi x plus 40 over x minus 2 pi x plus 2x. So these two cancel out. And our final perimeter is left with 40 over x plus 2x. And we can see that that is equivalent to that. So we finished the first part of this question successfully. Okay, so looking at part 2 of this question, which is worth 5 marks instead of the 4 of the previous question. So given that x can vary, find the minimum value of p, justifying that this value is a minimum. So we can tell this is differentiation because given that x can vary, and we have to find a minimum value, which hints at stationary points. But since it's in a more practical application, this is considered to be optimization because we're looking at the practical aspect of stationary points. And we have to justify it's a minimum. That also suggests the second derivative test because we have to make sure that it's a minimum. Since it's not a symmetrical function, it's not like x to the power 4, x to the power 6 or something like that, we can use the second derivative test. It won't give us an error of an answer. So I've just written here again, p equals 2x plus 40 over x, because that's the function we're going to be differentiating. Because they want the minimum value of p, and this is p. So dp over dx, that's the way of writing the differentiation for this equation, is 2 plus, and then better to write 40 as 40 over x is equal to 40x to the power of negative 1. That'll be easier for us, which makes it not 2 plus, but 2 minus 40x to the power of negative 2, which is equal to 2 minus 40 over x squared. Now, to find the minimum value, we set it to 0. 2 minus 40 over x squared is equal to 0. We get 2 is equal to 40 over x squared. Oops. Which gives us that 2x squared, if we multiply everything by x squared, is equal to 40. Let me write it over here now, which is equal to x squared is equal to 20 if we divide everything by 2, which means x is equal to plus or minus root 20. But it's probably going to be plus root 20 because we're working with a practical value of a badge. So x is equal to root 20. We can't have a negative length for the badge because, as we see in the diagram of the badge, the radius of the semicircles are root 20. And root 20, are x. And x has to be root 20. It can't be negative root 20. So now, using the value of x that we got, we need to find the minimum value of p. So we just substitute into the original equation, which is over here. So we get p is equal to 2 root 20 plus 40 over root 20. And that's equal to 2 root 20 plus 20 over root 5, which is equal to, and we can just use a calculator to find exact value. Or the decimal value, rather. Plus 20 root 5. That's equal to 8 root 5, which is equal to 17.89 cm. So that's our minimum value. But before we finish, we have to actually justify that this is actually a minimum. The way we do that is we use a second derivative test. So we take our second derivative, which is 2 minus 40 x to the power of negative 2. So dp over dv is, dp over dx is 2 minus 40 x to the power of negative 2. So d squared p over dx squared, in other words, the second derivative, is 80 x to the power of negative 3, which is equal to 80 over x cubed. So now we just substitute our value of x in, which is root 20. So 80 over root 20 cubed. And we don't even need to know what the exact value is. All we need to know is that since this is positive and this is positive, we have a number that's greater than 0. And if it's greater than 0, that means we have a minimum, according to the rules that we'd stated in the stationary points unit. If it's greater than 0, it's a minimum. If it's less than 0, it's a maximum. And if it's equal to 0, if the second derivative is equal to 0, then it's an inflection. But right now we have a minimum. So to conclude, p min, the minimum value p, is 17.89 cm. And that's our final answer. So thanks for watching this video and see you in the next one.